Here in this section we have the mean value theorem, theorem 3, Rolle's theorem. Suppose that y equal to f of x is continuous over the closed interval a comma b and differentiable at every point of its interior open interval a comma b. If f of a equal to f of b, then there is at least one number c in open interval a comma b at which f prime of c equal to 0. Rolle's theorem says that a differentiable curve has at least one horizontal tangent between any 2 points where it crosses a horizontal line. It may have just one, what we have here in part A, or it may have more, what we have here in part B. So here on the left side for part A, we have these 2 points, A, B, and here we connected A and B using this horizontal line. So what we have here on this part, this point is f of A, and that is equal to what we have for this point. So f of B is same as what we have for f of A. So it's same point here on y-axis. So on this part we have f of a equal to f of b, then there is at least one number c, which is this one, in this open interval ab, at which f prime of c is equal to 0. So here we have this tangent line, and this point f prime of c is equal to 0. Now what we have here on right side for part B, here again we have these 2 points, A, B, and here again f of A is equal to f of B. So based on this curve, we have 3 tangents. So one for this part, what we have for C1, here on top f prime of C1 is equal to 0. And what we have for C2, here we have this tangent line. So based on that, f prime of C2 is equal to 0. And for C3, we have, if you try to draw this vertical line and cross this curve, this point, here we have this tangent line. Here on this part, we have f prime of C3 is equal to 0. So all of these points, C1, C2, and C3 are between A and B. So here in this case, we have more than one horizontal tangent. There may be no horizontal tangent if the hypothesis of Rolle's theorem do not hold. Here on this part, this is discontinuous at an endpoint of closed interval A, comma B. So on this part, we have open circle. Because of that, this is discontinuous. Part B, again, this is discontinuous. But in this case, here we have open circle. So discontinuous at an interior point of closed interval A, comma B. In part C, this is continuous on closed interval A, comma B, but not differentiable at an interior point. Rolle's theorem may be combined with the intermediate value theorem to show when there is only one real solution of an equation f of x equal to 0. The intermediate value theorem. Suppose that f of x is continuous on the closed interval a, comma b, and that uppercase n is a number between f of a and f of b. Then there must be a number c in the interval a, comma b, so that is closed interval, for which f of c is equal to capital N. Based on what we have here on left side, we have closed interval a, comma b, So here is A, here is B. We have this curve, and this capital N is between f of A and f of B. Now, trying to find a number C in this closed interval. So here I have this point, drawing this vertical line, trying to cross this point or curve. So here we have C between A and B. In this case, f of C is equal to N. And here on right side, we have this curve. Here again, we have A, B. And we have this horizontal line based on what value we have here on y-axis, that is capital N, and that is between f of A and f of B. Now trying to find a number that is in this closed interval. So here we can have this point, drawing this vertical line, trying to cross this point. So here we have what we have is f of C1 is equal to capital N. We have more than one. So here is C2. Here again, crossing this curve, where we have our value for this point, capital N. So that is f of C2 equal to N. We have another one, which is this point. C3 is between A and B. Based on that, this point, f of C3 is equal to capital N, and capital N is between f of A and f of B. So here in this case, we had more than one number in this closed interval for which f of C was equal to capital N. The mean value theorem. Suppose y equal to f of x is continuous over a closed interval a comma b and differentiable on the interval's interior open interval a comma b, then there is at least one point C in open interval a comma b at which f of b minus f of a divided by b minus a, that is equal to f prime of c. So this f prime of c is slope, and here on this part we have these 2 points a, b based on what our interval is. Here connecting these 2 points, we have a and b on this curve. Connecting these 2 points, we have secant line. So what here we have, the mean value theorem says that somewhere between a and b, the curve has at least one tangent line that is parallel to secant line. So here on this curve, we have this tangent line, which is parallel to what we have for secant line. Corollary 1, if f prime of x equal to 0 at each point x of an open interval a comma b, then f of x is equal to c for all x belong to open interval a comma b, where c is constant. So what we have here on this point says that derivative of a constant is equal to 0. Corollary 2, if f prime of x equal to g prime of x at each point x in an open interval a comma b, then there exists a constant c such that f of x equal to g of x plus c for all x belong to open interval a comma b, that is, f minus g is a constant function on open interval a b. So here on this part we have this blue curve that is y equal to f of x, and the secant ab is the graph of function g of x. So this one in yellow, that is g of x. The function h of x equal to f of x minus g of x, that is the vertical distance between the graphs of f and g at x. So this one. And this part is the same as what we have here on top. So here on top, c is equal to f of x minus g of x. But in this case, we have this function h of x. But here on top, we used this c for constant. So this is vertical distance between fx and gx. Examples: find the value or values of c that satisfy the equation f of b minus f of a divided by b minus a equal to f prime of c in the conclusion of the mean value theorem for the following function and interval. F of x is equal to 2x squared minus 5x minus 3, and we have closed interval -2, 3. So first step, we have to find f of b and f of a. In this case, what we have here on this part, that is a, and here is b. So evaluate our function for -2 and +3. So first I have f of a that is equal to 2a squared minus 5a minus 3, and a is -2, and that is equal to 2 times -2 squared minus 5 times -2 minus 3. So f of -2 is equal to 15. Now finding f of b. So that is equal to 2 times b squared minus 5 times b minus 3. Now b is +3, so f of 3 is equal to 2 times 3 squared minus 5 times 3 minus 3. So f of 3 is equal to 0. The next step, we have to find f prime of c, but first we have to find f prime of x. So f prime of x is equal to 4x minus 5. Now we have to simplify f of b minus f of a over b minus a equal to f prime of c. So what we had for a and b and f of a and f of b here on top. I'm going to substitute those numbers. So f of b is 0, f of a is 15. 0 minus 15 here on top, and denominator we have b minus a, so it's 3 minus -2 equal to f prime of c is based on what we have here for f prime of x. So instead of x use c, we have 4c minus 5. So this is equal to, this part is equal to 4c minus 5. So we have -15 divided by 5 equal to 4c minus 5. Here -15 divided by 5 is -3, so that is equal to 4c minus 5. Now we can solve for c. So solving for c, here we have 4c equal to 5 minus 3, 4c equal to +2, and c is 1/2. So this is our final answer. Show that the equation f of x equal to x to the 4th power plus 5x plus 1 has exactly 1, 0 in the interval -1, 0. So here we have closed interval. First we have to evaluate our function based on what we have for endpoints -1 and 0. So finding f of -1 and f of 0. So here f of -1 is equal to -3 and f of 0 is equal to +1. According to the intermediate value theorem, f of x equal to x to the 4th power plus 5x plus 1 has at least 1 0 in the given interval. Now we have to use Rolle's theorem. So on this part, what we have is that our function is continuous over the closed interval and differentiable at every point of its interior interval. If f of a equal to f of b, then there is at least one number c in open interval at which f prime of c equal to 0. So we have to find f prime of c, and that should be equal to 0. If not, that means our function has no more than 1 0. So if there were even 2 points a and b, where f of x was 0, Rolle's theorem would guarantee the existence of a point x equal to c in the interval where f prime of x was 0. But the point is finding derivative of f of x, and f prime of x is equal to 4x cubed plus 5, and this is never 0, or in other words, this is always positive. But that means f has no more than 1 0, or in other words, f has exactly 1 0 in the closed interval -1, 0. Find all possible functions with a given derivative. F prime of t is equal to cosine 4t plus sine t divided by 3. So here on this part, we have to determine the functions that have same derivatives as the terms of sum. So here on this part, we have to find the trigonometric function that has the derivative cosine 4t and sine t over 3. So f of t is equal to, here I'm using this 1 4 to the left side, but we have to use reciprocal of what I have here. So reciprocal of 4 is 1 over 4. Then here we have cosine, I'm going to use sine 4t. Note that derivative of cosine is negative sign, but here what we have on top, that part is derivative. So I'm not going to have negative for f of t. And then here we have sine. So in this case, we're going to have negative. Do the same thing. Here we have 1/3 times t. Reciprocal of that one is 3. Here we have sine, but we're going to have negative cosine. And then use that one, t over 3. So f of t is equal to 1/4 sine 4t minus 3 times cosine t over 3 plus c is constant. So this is our answer. Find the function with a given derivative whose graph passes through the point P. So here we have r prime of theta equal to 2 minus cosecant theta times cotangent theta over point is pi over 2, 4. So what we have here for derivative, here on the first part we have 2. So derivative of 2 theta with respect to theta is equal to 2. So this is what we have for the first part. And second part we have negative cosecant times cotangent. So for that part we have derivative of cosecant with respect to theta, that is equal to negative cosecant times cotangent. So this is what exactly we have here on top. That means this is our answer for that part, meaning that derivative of 2 theta plus cosecant theta with respect to theta, that is equal to 2 minus cosecant theta times cotangent theta. So that means what we have for our function r of theta is equal to 2 times theta plus cosecant theta plus c for some constant c. So we have this constant here because derivative of constant is 0, and we may have 0 on this part, so we always using constant here on this part. Now next step, we have to use this point. So what we have is that r of pi over 2 is equal to 4, and now use this pi over 2 here on this part for theta. So we have r of pi over 2 equal to 2 times pi over 2 plus cosecant pi over 2 plus c. And based on what we had here, this part is equal to 4. Now we can simplify. So here 2 divided by 2. Here on this part we have pi plus cosecant pi over 2. That is equal to 1. So here we have pi plus 1 plus c equal to 4. Solving for c. C is equal to negative pi plus 3. Now use our function and substitute c, which is negative pi over 3. So our final answer is r of theta equal to 2 theta plus cosecant theta minus pi plus 3. On a certain planet's moon, the acceleration due to gravity is 3.2 meter per second square. If a rock is dropped into a crevasse, how fast will it be going just before it hits bottom 40 seconds later? So what we have here on this part, acceleration due to gravity is 3.2. So what that means, the velocity v of t as a function whose derivative is equal to this number, 3.2. So we're going to have v of t equal to 3.2 times t plus c for constant. Because the rock is initially at rest, v of 0 is equal to 0. So we have to substitute 0 for t and v of t and solve for c. So what we have, v of 0 is equal to 3.2 times 0 plus c, and that is equal to 0 based on what we have here. So 3.2 times 0, that is 0, plus c equal to 0. Here c is 0. Therefore, the rock's velocity function is v of t equal to 3.2 times t. Because the rock hits the bottom of crevasse at 40 seconds, I'm going to substitute 40 for t and simplify to find rock's velocity at the bottom of the crevasse. So here we have v of 40 equal to 3.2 times 40, that is equal to 128 meter per second. So this means the rock's velocity at the bottom of the crevasse is 128 meter per second. Given the velocity v equal to derivative of s with respect to t and the initial position of a body moving along a coordinate line, find the body's position at time t. So velocity is equal to 9.8 times t plus 10, and s of 0 is equal to 15. So v is equal to derivative of s with respect to t. We have to find s of t. So based on what we have for velocity, s of t is equal to, here power is 1, so add 1. We're going to have t squared, and then use that power 2. So 9.8 divided by 2, here we have 4.9. So we have 4.9 times t squared plus, here we have 10t So I did the same thing on this part. Here we have t, and that is power 0, adding 1. Now we have 1 as a power. Use that one here in the denominator, 10 divided by 1, so we have 10 times t. Then plus constant. Now use s of 0 equal to 15 to find constant c. So s of 0 is equal to 4.9 times t is 0, so 0 squared plus 10 times 0 plus c. S of 0 is 15, so 15 equal to 4.9 times 0 squared plus 10 times 0 plus c. Solving for c, c is equal to 15. Now use 15 here on this part to find s of t, that is equal to 4.9 t squared plus 10t plus 15. So this function is our final answer, and that is lattice position at time t.